In this section, we're going to talk about some properties of trees. And the first thing we're going to talk about is this theorem that I think we mentioned a little bit earlier, and that is this theorem that says there is a unique path between every pair of vertices in a tree. So they go over in the side books, they go over the proof for that. And I'm not going to just read this word for word, but I'm going to kind of just go over what they're saying about how this is proven. Okay, so we're going to say that there's so again, we're trying to prove that there's a unique path between every pair of vertices in a tree. So we're going to say that there's a tree that has two vertices U and V, and you see the picture here. And what we're going to do is we're going to prove this by contrapositive. So we're going to assume that this theorem is not true and then find that it leads to a contradiction. Okay, so let's assume that this is not true, that there are two vertices U and V in any tree, and that there would be, let's assume that there is more than one way to get from U to V, more than one unique path. And so what they have here is they just have a picture of a lot of different vertices, but then you're going along from U and you get to this one that they've labeled X, and we see that there's two different ways to go. We could go either way and then get back to Y eventually, and then go on to V. So they're saying we're assuming that this theorem is not true, so we're going to say that there's more than one path. So these are the two paths. Okay, so but here's what they say next. They say, if this is really true that we have two paths, then if we take a look at that vertex at which the two paths differ, when the point at which they go different directions, we'll call that the X vertex, and then we see where the two paths come back together, we'll call that the Y. Then we'll say that if that's really the case, that those two paths do exist, then we have what would be a cycle here, because we could start with X and follow along one of the paths to get to Y, and then get on the other path to get back to X. So that would be a closed walk that does not repeat edges and does not repeat vertices, except for the first one that is the same. And that's a cycle. And remember, the definition of trees that you see here at the top says a tree is an undirected graph that is connected and has no cycles. So if we assume this theorem is not true, we find that there is a cycle involved there, and then that would mean that it's not a tree. So therefore we came up with a contradiction, so therefore we have to assume that we have proven that this theorem is true, and that we can now know that there is just one unique path between every pair of vertices in a tree. Now notice we're not talking about direction. You could say, well, I could go from U to V, or I could go back from V to U, but we would consider that the same path since we're talking about undirected graphs. Now in Zybooks, they have this problem soon after they go over that proof. And I wanted to show you because if you don't understand what they're doing, it could be a little bit confusing. We just showed in that proof that we assumed there was more than one unique path, and then we found that that meant there had to be a cycle in there, right? So this problem here, it says this: the two sequences of nodes given below denote two distinct paths in a graph between vertices J and D. So right away they're saying we have two distinct paths. And so you might think, since we're in a section where we're talking about trees, and we just said that trees don't have any more than one unique path, then that might be confusing to you. So the idea is they're just saying, well, let's say that we have a graph not necessarily a tree. But let's say we have a graph and there are two distinct paths. Then they're going to lead you to realize that there is a cycle in there. So this little problem is just kind of illustrating that whole idea that we just went through in that proof of that theorem. Okay, so we're going to find out that this graph that they're talking about ends up not being a tree because it doesn't have one distinct path between J and D. So the two sequences of nodes given below denote two distinct paths in a graph between vertices J and D. So you see the two paths there. Then it says, which of the following answers describes a cycle that you can deduce is in G? So, now we're talking about cycles, and that's what ends up happening, that we could say that there's actually a cycle in here, and therefore it's not a tree. So we could first of all look at the first one, BAGIB. So if we go, we can see that we could go from B to A in that second path. We could go to B to A, we could go to A to F. Now, B to A, then A to G would be the next. Now there's no way to get to G from A, right? Because the only way to get to G in the first path is either by going through I or F. And there is no G in the second path. So we can't use any of the edges in these two paths to go and to go and get that cycle there. So we would say that that's not even possible. That first one's not even possible using these two paths. But then going on to the second one, BAFGIB. If we started at BAF in the second path, we could then jump up to the F in the first path and go backwards and do GIB. So we start out BAF and then from the F go to GIB. So kind of look at it this way here, that you go to BAF and then we go along that other path going back to the B, so GIB. So that actually does fall on those two paths there together. We could come up with that path, and that is a cycle because we aren't going to be going over an edge more than once, and we're not including a vertex more than once. You might say, well, what about these two F's in here? But what we would do is go from B to A to F, and then we would go from F to the G up in that first path. So we're not repeating vertices at all. So this one, the second one, would be the answer that would describe a cycle that we know is in G based upon these two paths. Now we might want to go on and just go on and look at this last one here, BAFECFGIB. So I'm going to start down in this second one again, BAF, and then we could go on to E and then go on to C. Then I could, since C is in both of these paths, I could jump to the first path and go then back, FGIB. So that path that we have here, BAFECFGIB, that is in there. We could deduce that that would be a possible way to get through to follow along within that graph. But it's not a cycle because the F appears twice here. So it definitely, it's a circuit, but it's not a cycle. So that's why we would rule out this third one here. And so so this third one here, it's not a cycle, it's a circuit. So our answer would be that second one. And again, that's not talking, it turns out then because of this that this graph they're talking about is not a tree. Okay, so let's talk about a little bit about free trees because we've talked a lot about rooted trees now already. You know, we said there's a root at the top, and then we've got descendants and ancestors and children and parents and so on. But it's a little bit different when we're talking about free trees. Remember, free trees were that other kind of tree that we talked about early on, and that's one that it's still a tree because it's a connected graph, and it doesn't have any cycles, but we don't have this organization where it starts from one vertex and then keeps branching off. So that's what a free tree is. Now, if we were talking about rooted trees, we actually already said that the term leaf in a rooted tree was a vertex with no children. Okay, we said if we get down to a vertex has no children, that's considered a leaf. But what about in free trees? Well, it turns out that we can come up with a definition to then be able to say what a leaf is in a free tree. So we'll talk about what that is now. The reason why it has to have a different definition is because the reason it has a different definition is because there is no such thing as children in a free tree. Okay, so here's the definition of a leaf in a free tree. It is a vertex of degree 1. And then unless the tree has only one vertex. So, you know, if it was a very simple little tree, all it has is one dot. No edges, but just one little dot. Then we would say that dot is a leaf, okay? And it doesn't have a degree 1, right? It would have a degree 0 if there's no edges in that graph. So if it's that simple special case where the tree only has one vertex, then this is not true. It would be a leaf even though it doesn't have a vertex of degree 1. But if it's anything more than just one dot, then that means that that it has more than one vertex. And so therefore we would say if that's the case, then we would define any vertex of degree 1 to be a leaf. So let's look here. We've got some special cases of these free trees with special names, just like we had some special names with when we were talking about just graphs in general, when we talked about complete graphs with the capital C and then the capital K. Well, if we have a tree that looks like this P, we're going to call this one P sub 5. It's just one little path with, in this case, 5 vertices. But if we have a path like that and it has a different number of vertices, then we would have the subscript represent how many vertices there are in there. So if I talk about a P sub n, that would be a free tree that's just one little path like this with n vertices. Now, if n is greater than or equal to 2, let's think about how many leaves there would be in P sub n. So the reason we're saying n greater than or equal to 2 is we're not going to consider that situation where a tree is only one little dot. Okay, so we're assuming there's at least 2 vertices and connected vertices in the trees that we're going to look at. How many leaves would we say there are? Well, first of all, let's look at this one. We see that there's 2 leaves in the P sub 5 because the ones on the ends are the ones that have degree 1. All the others have degree 2. And if you think about it, what about a longer graph that has more vertices but still is just this one long path like this? You'd realize that there's still going to just be 2 leaves. The ends are the ones that are going to have degree 1. So we would say 2, no matter how many vertices, P sub n is going to have 2 leaves. How many edges are there in P sub n? Well, let's just look at the one we have here, P sub 5. We have 5 vertices and only 4 edges. And if you think about it, if you had more vertices, we'd still have the same situation that we're going to have one less edge than we do vertices, right? So it would be n minus 1. If I had 10 vertices lined up and connected them all together just in one little path, we would need 9 edges. So it's always going to be the n minus 1. Another special kind of a free tree is called a star graph, and we use a capital S for that, and the K stands for not actually the number of vertices, so this can be a little bit confusing. This picture that you see down here, that's an S sub 5. Notice that there are 6 vertices there. So what a star graph consists of a single vertex connected by an edge to k other vertices. So that's why this graph here is called a S5. It has one vertex in the middle and then edges connecting to 5 other vertices. So when we have an S sub 5, we actually have 6 vertices. If I had a vertex with 10 vertices around and that middle vertex is connected to all 10 of those, that would give me one extra vertex. So if I have an S10, it's going to actually have 11 vertices. So would we consider S sub k, k being any number, a tree? Well, looking at this picture here of this one and imagining what others would look like, we would probably say, yeah, that's pretty obvious that it's a tree because there are no cycles in there. We can't get from one vertex back to itself without retracing our steps, because for a cycle you can't retrace steps or go back through vertices. So there's no way to do that here, so we would say that it is a tree. S sub k would always be a tree. Okay, how many vertices are there in S sub k? So we already kind of talked about that. So in this S sub 5 there were 6 vertices. We're always going to have one more vertex because we start with that one in the middle and then we connect it to k vertices. So it would be k plus 1. Now, how many edges are there in a star graph with n vertices? Okay, so n now is not that subscript on the S. N now is actually the number of vertices. So in this S5, we've got 6 vertices. And how many edges? 1, 2, 3, 4, 5. One less edge than there are vertices. And it turns out, if you can imagine other vertices there too, there's always going to be one less edge than the number of vertices, because that middle vertex connects to all of those other vertices. So it would just be the number of vertices n minus 1. Okay, we have another theorem that talks about how the number of edges and the number of vertices relate. So it says, let T be a tree with n vertices and m edges. Then m is going to equal n minus 1. So this means we'll always have one less edge than we have vertices. We're not going to prove it, but you can look here and see these examples here. This first one, the P sub 5, it has 5 vertices and only 4 edges. S5 has 6 vertices and only 5 edges. And something like this other one over here, we could count the vertices and edges. There's 10 vertices and only 9 edges. So looks like it might be true. We haven't proven it, but we're just going to accept that this is true. I don't remember if Zybooks goes over the proof for that or not, but we're just going to take it as truth here. Now, what is a forest? A forest, if you think about a forest in real life, it's just a collection of trees, right? Individual trees, collection of individual trees, more than just one little tree. And that's the case here too. A forest is a graph that has no cycles and is not necessarily connected. The picture below here shows a forest with 3 connected components. So each of these components are connected within itself, but the 3 components all together don't get connected, okay? So we have these 3 separate trees here. And so since they're all trees, we know there are no cycles involved here. And therefore, we would say that that's a graph with no cycles. And it's not necessarily connected. So that's why we could call it a forest. So let's think about the answers to some questions here. How many vertices are there in the forest pictured above? Okay, so we could take a look and just count for each of these trees. So there's 4 vertices in the first one. We'll call that n sub 1. And then n sub 2 would be how many vertices in the second tree. There would be 3 there, and 4 in n sub 3. So in the third tree, so we'd say n sub 3 is equal to 4. So we could add them all up and get 11. So our answer would be 11. Now let's ask this. How many edges are there in the forest pictured above? Well, there are 3 edges in the first one, 2 edges in the second one, 3 edges in the third one. And notice what we just talked about is true here, that there's 1 less edge in each tree than there are vertices. So 4 vertices, 3 edges for the first one. 3 vertices, 2 edges for the second, and so on, okay? So always 1 less edge than the number of vertices. So how many edges are there in that forest? We could either add them up, or we could say, well, there were 11 vertices, but there were 3 trees. So for each tree, we would have to subtract 1 to get the number of edges. So we could do it that way too. So we'd say 8 is the answer there. Now it says, suppose that we have a forest with n vertices and c connected components. So basically c different trees, okay? Give a conjecture for the number of edges in the forest as a function of n and c. Well, look down here where you see in red it says edges, and this is talking about the number of edges in this example here. We found the number of edges in the first tree was n sub 1 minus 1, because again we just subtract 1 from the number of vertices. The number of edges in the second tree was n sub 2 minus 1. The number of edges in the third tree was n sub 3 minus 1. When we added all those up, if we say that the total number of vertices is n, then that ends up being n minus 3. We had to subtract 1 for each tree that was in there. Okay, so that's what happened in this forest with 3 trees. So imagine just a general forest with C trees. We could add up the number of vertices in each tree and know that the number of edges is 1 less than the number of vertices in each tree. But since there's C trees, we would be subtracting 1 several times, C times, right? So subtract 1 and then do it again, do that C times, which is equivalent to subtracting the number C. So we might guess that it makes sense that the answer to this, the number of edges in a forest as a function of n and c, would be n minus c. Again, because n is the number of vertices and we had to subtract 1 for each tree to get the number of edges. So it's n minus c. And so I've already kind of gone over the proof there, but here it is up here on the screen. So it just says, let's say that we've got all these individual n's that add up together to give us the, we've got n sub 1 for the first tree, n sub 2, and so on all the way. Add all those together, we get the n. But then it says for when we look at the individual components, there's going to be the n sub j, depending on what j is, it might be the first tree, second tree, whatever, minus minus 1 edges. We have to subtract 1 for the number of edges. And then, but since we do that c times, that ends up turning into being n minus c. Just like here you see at the bottom again, we had to subtract 1 3 times because we had 3 trees, so we ended up with n minus 3. So if we have c trees, we would end up with n minus c. So that's how we could think that through and figure that out for sure.